Urea is an organic white compound manufactured worldwide in various shapes and sizes. It is produced from ammonia and carbon dioxide. It is most commonly used by the agriculture industry as a fertilizer, but is also used as an intermediate product in the production of melamine and has thus found uses in the manufacture of plastics. Due to its importance in farming, the technology to commercially produce urea dates back to the early 1920s. Urea is in many ways the most convenient form for fixed nitrogen. It has the highest nitrogen content available in solid fertilizer, which is 46%. Urea is easily produced as pills or granules and is easily transported in bulk or bags with no explosive hazard. It leaves no salt residue after use on crops as well. There are various processes to manufacture urea. In this assignment, Snapprogatti ammonia stripping process is selected because it involves a high NH3 to CO2 ratio in the reactor. Now, let us take you through the process flow diagram of a urea production process. First, at the high pressure section, the CO2 is fed directly into the reactor after it leaves the compressor, whereas the ammonia is fed to the reactor from the ammonia receiver in the medium pressure section of the process. To obtain a product that meets purity specifications, purification steps are needed. The first of these is the stripper. The stripper is a falling film heat exchanger which facilitates the decomposition of ammonium carbamate into ammonia and CO2. The off gases from the stripper are sent to the high pressure carbamate receiver, where they are condensed to form ammonium carbamate. Next, we are at the medium pressure section. This section contains only one unit for the purification of the urea solution, this unit being the medium pressure decomposer. The purified urea liquor then makes its way to the low pressure decomposer, and the resulting off gases are transferred to the shell of the preheater, where they are absorbed and react, thereby heating the endothermic reaction occurring within the unit. Finally, we are at the low pressure section. This is the last section that is aimed at the decomposition of ammonium carbamate to purify the product. This purification occurs within the low pressure decomposer. The vacuum evaporation section is, as the name suggests, aimed at concentrating the urea solution through evaporation of any remaining water. The urea liquor is transported from a preheater into the first vacuum evaporator through a heating element before making its way through to the pulling column. Now, we'll talk about the control strategies of three major equipments in the process. The equipments are distillation column, pulling tower, and heat exchanger. First is distillation column. The goal of a distillation system is to maintain an optimum production rate and the main specifications that are set for each product. The main control variables are distillate composition, column level, and column pressure. Manipulated variables are distillate flow, reflux flow, or bottom flow. And finally, process disturbances includes feed flow, feed composition, and feed temperature. For a distillation system, the term material balance means that the sum of material that leaves the column must be equal to the feed that enters the column. If the flows of material are not balanced, problems could develop in the process. Control loops of the control strategy includes feed flow control loop, bottom level control loop, overhead product level control loop, and an off-gas stream pressure control loop. Feed flow control loops controls the rate of feed flow into the tower. Bottom level control loop controls the level at the bottom of the tower by controlling the bottom's product flow. overhead product level control loop by controlling the overhead product flow. Off-gas stream pressure control loop control the release of gas from the overhead receiver, which controls the pressure in the distillation column. Primary energy flows are associated with heat transfer into or out of the system. For example, the heat input to the reboiler and feed preheater, and the heat that is transferred as overhead vapor in the condenser. Most of the heat input to the tower from reboiler and the feed preheater are removed by the condenser. Heat also leaves the tower in the products, in the gases that are removed from the system, and by heat transfer through equipment casing and piping. Secondary energy flow are associated with heat transfer, which the heat remain within the distillation system. For example, reflux transfer heat out of some of the vapors in the column and condenses the heavier components. However, the heat transfer is between two fluids within that distillation column. It doesn't involve an external medium such as air or cooling water. Primary energy flows are controlled by a reboiler temperature control loop, a feed preheater temperature control loop, and a condenser temperature control loop. The reboiler temperature control loop controls the amount of heat that is sent to the tower. This temperature control is accomplished by regulating the flow of steam through the reboiler. The feed preheater temperature control loop controls the temperature of the feed by regulating the flow of steam through the preheater. The condenser temperature control loop regulates the amount of cooling that takes place in the condenser. Major temperature changes in this control loop are accomplished by starting and stopping the fans in the condenser. Now, we'll talk about pulling tower, which is the second major equipment of the urea production process. The pulling of urea begins with the very accurate drizzle of melt droplets evenly spread across the cross-sectional area of the tower. Before reaching the bottom of the tower, the drizzle is cooled with the purified air, which also allows a soft landing of the crystallized prills. The exchange heat between the prills and the ambient airflow subsequently used to regulate the inlet air temperature at the bottom of the tower. Both the surplus of air and the anti-icing air is meticulously filtered before being exhausted or reused. This is an illustration of the proposed process control strategy for pulling tower. As you can see, there are two different control loops which are present in the pulling tower. Moisture content and the pressure of the tower are being controlled. The material balance of the pulling tower can be controlled by controlling the flow of the material. The feed-forward moisture control loop controls the amount of the feed flow into the overhead of the tower. When the moisture content sensor senses the increase of moisture content inside the pulling tower, the control loop will decrease the flow of feed into the pulling tower through a valve to adapt to the new condition. With less feed into the pulling tower, the overall moisture content inside the pulling tower decreases. The flow of outlet air at the overhead of the pulling tower is controlled by the off-gas stream pressure control loop. When the pressure sensor senses the increase of pressure inside the tower, the control loop will increase the opening of the pressure relieving valve to increase the outlet airflow. With lesser amount of air inside the pulling tower, the overall pressure is back to normal. Now, we have come to the third and final major equipment, which is the heat exchanger. Basic methods of control used by automatic process control systems is feedback control. In a feedback, control system is initiated after the control variable has deviated from the set point. In this system, steam is used to heat the water. The steam transfers heat, which enters the heater at the top, flows around the tube, and exits the heater at the bottom. The temperature of the water at the outlet of the heater is the control variable of the system. It is also the measured variable because the control system uses it as the basis for making operating changes. The manipulated variable in this system is the inlet steam flows, that is the steam flow into the heater. It is just to keep the outlet water temperature at set point. Temperature sensing device at the water outlet. More specifically, the device is the temperature sensor which contains a gas, and it will expand, and the temperature transmitter will sense it when the temperature of the water leaving the heater increases. The transmitter sends pneumatic signal that is proportional to the water temperature to controller. The controller measures this signal and compares it with the set point. The controller then computes the difference between the temperature of the water and set point and send corrective signal to the final control element, which is the control valve. Now we have talked about proposed feedback control system. What about a feed-forward control system? Would it be better? In the feed-forward control system, it attempts to correct the process disturbance before the control variable in the process deviates from the set point. The control variable in this system is water temperature at the outlet. The inlet water temperature is used to determine whether a control action is needed to maintain the outlet temperature. So, it is the measure variable in the system. If the water temperature at the inlet stream changes, the temperature sensor detects the change in temperature and changes the signal it sends to the transmitter. The transmitter measures the signal from the temperature sensor and sends a proportional signal to the controller. The controller measures the signal from the transmitter and compare it with the set point. The controller will send the signal to the control valve. The control valve will respond by opening or closing to change the amount of steam entering the system. If the water inlet is hotter than usual, the control system closes the control valve to decrease the steam flow into the system. As a result, less heat is transferred into the water and the desired temperature at the water outlet can be achieved. However, if the temperature of the inlet stream changes, the desired temperature at the water outlet cannot be able to achieve anymore. This control system can be corrected by combining a feedback system into it, which results a feedback and feed-forward control system. The feed-forward responds to changes in water inlet temperature, while the feedback responds to changes in the outlet water temperature, which caused by the surrounding disturbances.